Let us start this story with the example of a species with the scientific name Mnemiopsis leidii. It looks like a jellyfish, but in fact it belongs to a different but related group called the comb jellies, and it is commonly known as the sea walnut. It is a small organism having a maximum body length of roughly 7 to 12 centimeters and consumes zooplankton as well as eggs and larvae or fish. It is sometimes known to eat smaller individuals of its own kind. For its size, the animal can capture prey at the same rate as fish or even higher. This ability makes the sea walnut a major player in the oceans. The comb jelly was originally native to the western Atlantic coastal waters in North America as well as in South America, having predators including species of bird and fish. In Europe, the sea walnut first appeared in the Black Sea in 1982. In combination with other major events such as overfishing and pollution, it speeded up the collapse of the major fisheries in the Black Sea and caused millions of losses in the 1980s. In the Mediterranean Sea, it was first recorded in 1990 in the Gulfs of Saronikos and Elefsina in Greece and other parts of the Aegean Sea. This caused great concern. Indeed, it was not only the ecological problem this predator of zooplankton could pose to fish eggs and larvae, altering the food web at all levels, but the economic problems that it could cause as well. The sea walnut made its way into the Caspian Sea, where it was first recorded in 1999. After that, it was encountered all over the Mediterranean Sea. In the Israeli coast, sea walnut has been made responsible for blocking pipes of desalination and coastal power plants, forcing engineers to modify their designs, highly increasing the cost and expenses. Finally, it appeared in almost all European seas, including the Baltic Sea and the North Sea. Like the sea walnut, several other species appear outside their native distributional range and are called non-native or non-indigenous species. Most of them do not survive the new marine environment for long. However, when found in a new environment, free from natural pathogens, grazers, predators, parasites and competitors, they often develop fast to large population sizes. These high populations can outcompete the native flora or fauna, dominating their environment and thus become invasive alien species. In the Mediterranean, non-indigenous species increase at the rate of one every 2 weeks, and it is reported that around 1,000 are present. But how can this happen? What is the cause of the introduction and spreading of non-indigenous species? One main vector for introducing non-indigenous species is the international water transport. Nowadays, around 90% of the world's global trade is carried by the international shipping industry. About a fifth of those goods are loaded or unloaded in European ports, transported by large vessels such as cargo carriers, tankers, and container ships. These ships use ballast water in order to provide stability and maneuverability for the vessel during voyage and to control the draft of the vessel. Typically, ballast water is taken on in the coastal waters in one region at the source port. However, ballast water contains a variety of biological materials, including plants, bacteria, microbes, small invertebrates, egg cysts, and larvae of various species. At the destination port, ballast water is typically discharged into the environment as cargo is taken on. According to estimates, over 7,000 different marine species are transported worldwide every day through ballast water. Another important vector for the transfer of non-indigenous species is hull fouling, also called biofouling. It is the undesirable accumulation of microorganisms, plants, algae and animals on submerged structures and especially on ships' hulls. Some of these organisms are then detached from the hull by hydrodynamic forces when the vessel is traveling at a sufficiently high speed. Newer research results suggest that biofouling may be more environmentally damaging than invasive alien species relocated through ballasting operations. Keeping of the ship's hull clean is important also because marine biofouling affects the performance of ships, increasing fuel consumption and thus reducing the profitability of ship transport. A common technology which addresses the problem is to use a specialized coating, such as anti-fouling paint, applied to the hulls of the ship. It has the ability to slow the growth of subaquatic organisms attached to the hull. In common practice, anti-fouling paints are formulated with biocides, which are toxic chemical substances usually based on copper. Scrubbing a hull with sloughing bottom paint while it is in the water releases its biocides and the attached biofouling into the environment. One way to minimize this environmental impact from such a treatment is to hull out and clean the vessels at boat yards with a closed-loop system. Other environmental friendly technologies include brushes, which are able to clean the hull in the water and simultaneously suck the detached layer and contaminated water. Coming back to the main activity that causes the introduction and spreading of invasive alien species, let's go up and down the value chain to see which other activities play a major role in this problem. As we have already identified earlier, the international sea and water transport plays a central role, contributing to the release of non-indigenous species through ballast water and sediment discharge and through biofouling. Exploring further the structure of international seaborne trade, we see that mining and quarrying is the main industry that uses seaborne trade for its products, such as crude oil, gas, coal, iron ore, cement, gravel, stones, etc. The shipbuilding industry provides the means for the transport, such as bulk carriers, container ships, and tankers. On the other hand, considering the volume of products transported from the European and to the European ports, one identifies the manufacturing sector as a major player at the end of the value chain, with most important industries the coke and refined petroleum industry, chemicals and basic metals. But these are not the only activities related to the introduction and release of invasive alien species. Other activities are equally important, such as fishing and recreational activities in coastal waters, port-based deballasting, retrofitting older ships with ballast water management systems, hull scrubbing and wiping off fouling from the ship's hull, coating and painting the hull with anti-fouling systems. So far, we have identified the main activities for the introduction and spreading of invasive alien species. Let's now reveal the main actors and stakeholders behind these activities, playing a direct or indirect role. We could overall group them in four main clusters: professional actors, regulative actors, social actors, and individual actors. We can identify several professional actors working directly in the water transport sector, such as ship officers, ship owners, and charterers, others that are involved in the shipbuilding sector, many industrial sectors, but also professionals operating in coastal waters like cruise and leisure companies and fishermen. We then have regulative actors like European national regulators and various authorities, social actors such as NGOs, yacht clubs, etc., who also influence in a way the sea and coastal water transport. Finally, it is all of us, consumers, who influence with our behavior all these activities. But from all these actors, who might be the most important and influential? Who is the one who should change his behavior, and in which way it needs to change? In order to answer these questions, we have analyzed a number of criteria, including the influence of this actor on activities linked to pressures, his impact on other key actors, the degree of independence in his decision related to the pressures, and how likely or feasible is a behavioral change of this actor. According to these criteria, it seems that ship owners are a major target group. They are directly involved in decisions related to many of the key activities. They influence other key actors, and they are relatively independent in their decisions. In fact, ship owners are the ones who decide which technologies to install in new ships regarding ballast water treatment, whether to retrofit older ships with effective ballast water management systems, and when, which anti-fouling treatment to use, how and when clean off the ship's hulls, which shipping routes to select. All these decisions may affect the introduction of invasive alien species in a region or their spreading from one coastal region to another. Furthermore, they are in a position to influence other key actors like ship officers, naval architects, and shipyards, and through their associations, they can leverage the decisions of national and international legislators affecting the seawater transport. Another actor, which is also among the most influential group of actors, is the national and European legislators. They play a major role when it comes to ratifying international treaties and conventions, applying national or international regulations, improving environmental systems such as ballast water management systems, regulating business sectors which are crucial for water transport, and controlling the fleets of naval forces which operate in various seas. They also do influence other main actors in their decisions, including ship owners and charterers, international bodies like the International Maritime Organization, national registries, port authorities and other agencies, industries, and most notably the mining and quarrying and the manufacturing industry, which are especially important for the international ship transport, and of course the Navy. A third group, which seems to be increasingly influential, are manufacturers involved in the construction of specialized marine equipment and the production of chemical products. The marine equipment suppliers and manufacturers provide effective systems that clean ballast water from microorganisms, the so-called ballast water treatment systems, produce special hull coatings keeping the hull fouling free as much as possible, contribute to other promising innovations and technologies that might reduce the risk coming from invasive alien species, but are dependent on other actors like ship owners and national or international legislators. As a final step in this presentation, let's now investigate what are some of the recent and current legal responses to address the challenge of invasive alien species. The European Union, recognizing the threat that non-indigenous species pose to biodiversity, ecosystem balance and human health, initiated a number of legal responses. The Marine Strategy Framework Directive, adopted in 2008, identifying non-indigenous species as a descriptor for assessing good environmental status of marine waters. EU Regulation No. 1143/2014 outlines an invasive species strategy aimed at reducing impacts by focusing on early detection, eradication and management of problem species. At the international level, the International Convention for the Control and Management of Ships' Ballast Water and Sediments will enter into force in September 2017. Since it is binding for all 172 member states of the International Maritime Organization, it will be the most significant international legal initiative to prevent the spread of harmful aquatic organisms from one region to another. It will establish standards and procedures for the management and control of ballast water and sediments. From then on, all ships will be required to implement a ballast water and sediment management plan and carry a ballast water record book. Unfortunately, no similar international regulation apply to hull fouling, although research results suggest that it may have an equal or greater impact to the environment. The International Convention on the Control of Harmful Anti-Fouling Systems on Ships, which came into force in 2008, focuses on the prevention of adverse impacts from the use of anti-fouling systems and the biocides that may contain, rather than on the prevention of the transfer of organisms through hull fouling. Following the aforementioned legal and regulatory developments, and supported by major advances in science, a number of technical responses have also emerged to deal with the problem of IAS. In the last decade, highly specialized companies have started to offer ballast water treatment systems. However, as you can see in this graph, although the rate of new-built merchant ships that have an onboard ballast water treatment system has increased after 2010, the overall percentage is still low. For example, only 20% of the new oil tankers have installed ballast water treatment systems. So, what are the necessary technical responses? Obviously, the majority of merchant ships currently in operation are not equipped with any ballast water management system and will need to be retrofitted. The costs for this retrofitting are still high, ranging from few €100,000 for small systems to 2 million for the largest ones. Additional costs are required to operate and maintain the system as well. Recent promising innovations in the field of hull coating and anti-fouling paints may help to keep the ship's hull clean as much as possible, reduce biocides or even use biocide-free paints. These need to be further promoted. New techniques in water hull cleaning and filtration systems may reduce the release of microorganisms to the sea and also need to be further pursued. This concludes our presentation. We hope that you enjoyed it and we thank you for your attendance.